Welcome to qnawire.
In this problem, we are going to let L be the length of the tube and the rod, and point O be the point of intersection of the tube and the axle. So the first thing we are going to do is write down our moments of inertia. So the moment of inertia for the tube, IT, is equal to 1/12 times the mass of the tube times L squared. And the moment of inertia for the rod, IR, is equal to 1/12 times the mass of the rod times L squared. So both of these have the same shape. And so the forms of the moments of inertia are the same. Now, by kinematics, we are going to write down the r and theta components of their velocities. So the theta component of the velocity of the tube, Vt, is equal to the center of the tube, Rt, times its angular speed, omega. And this is L/2 times omega. Now the same for the theta component of the velocity of the rod, v theta subscript r. This is equal to the center of the rod, r bar, capital R, times the angular speed, omega. And this is equal to L/2 plus the distance x, which is when the rod sticks out of the tube, multiplied by omega. And finally, the r component, Vr, for the tube is simply Vr. So it has some magnitude Vr. So Vr is the speed of the rod relative to the tube, and that's what we wish to calculate for in this problem. So the next thing we'll do is find the angular momentum about point O. So the angular momentum about O is represented by h. H about point O is equal to the mass of the tube times the center of the tube times the velocity v theta, and that's for the tube, plus the moment of inertia for the tube times omega, plus the contribution from the rod, which is the mass of the rod times the center of the rod, rr, times the theta component of its velocity, v theta r, plus I omega, the angular momentum contribution from the center of the rod, ir omega. And so this we can write, if we expand out our r values, or r times v values, we get this to be mt, the mass of the tube, times L/2 times L/2 omega, plus 1/12. So all our expressions above for the moments of inertia and the velocities can now be substituted in here. So 1/12 mt L squared omega plus mr into L/2 plus x into L/2 plus x times omega, plus the last term, which is 1/12 mr L squared omega. And so we can write this, since we can see that omega is a common factor, we can write this as follows. So this is 1 over 3. If we simplify, mt L squared plus the mass of the rod, mr, into 1 over 3 L squared plus Lx plus x squared, all this times the common factor omega. So that's the angular momentum about point O. The next thing we'll do is find the kinetic energy. So the kinetic energy of the system is T, and T is equal to a half mt times v bar theta t squared. It's a half mv squared plus the contribution from the angular momentum, a half I t omega squared, plus the contribution from the rod, which is a half times the mass of the rod times v theta squared plus a half mr vr squared. So for each component of the rod, plus a half times the angular momentum contribution ir omega squared. And so this can be written as, we'll bring out the half as a common factor into mt, and again we'll substitute for our velocities, L over 2 omega all squared plus 1 over 12 mass of the tube, L squared omega squared plus a half mr into L over 2 plus x all squared times omega squared plus a half mr vr squared, that term stays the same, plus the final term is 1 over 12 mr, the mass of the rod, L squared omega squared. And so we can go one better in simplifying this. So we can write this as a half into 1 over 3 mt L squared plus mr into 1 over 3 L squared plus Lx plus x squared, and we can bring out a common factor there for these terms of omega squared. Plus a half mr vr squared. And if we go to our term above for the angular momentum about point O, we can see something quite useful, that this is simply a half times the angular momentum about point O multiplied by omega. So this is common factor omega squared, and that was the common factor omega, and the term in brackets is the same, plus the extra term, a half mr vr squared. So that's our kinetic energy, and we've written our kinetic energy in terms of the angular momentum. The potential energy is 0, since all the motion here is horizontal. V is equal to 0. So now let's look at our angular momentum for states 1 and states 2. So we've written out in a general expression for angular momentum and our kinetic energies. Now, state 1 is the state in which x is equal to 0, so the rod is completely in the tube. The angular momentum omega is equal to, we'll call it omega 1, and that's 5 radians per second, and Vr is equal to 0. So the speed of the velocity of the rod with respect to the tube is 0. So in this state, the angular momentum of the system about point O subscript 1 for state 1 is equal to 1 over 3 into the mass of the tube plus the mass of the rod, L squared omega. And this is 1 over 3, and we substitute our values in here, into 6 plus 4, the mass of the tube plus the mass of the rod, times L squared, which is 0.8 meters squared, times omega. The angular frequency is 5 radians per second. And so we get the initial angular momentum to be 10.66667 We're keeping as many decimal points as we can, and that's kg meter squared per second. So that's the angular momentum about point O. The kinetic energy T1, remember we're just using our equations that we found above. That's a half into 1 over 3 into mt plus mr times L squared omega squared plus 0. So mr/vr was just a half, mr/vr squared was just 0. So that's a half times, remember, HO in state 1, the angular momentum about O, times an extra omega. So that's a half times the value of the angular momentum, which we calculated to be 10.6667 times the angular frequency of 5. Hence we get the kinetic energy in the first state when x is equal to 0 to be 26.667 joules. And we also know that V1 is equal to 0. So that was state 1. Now let's do the same for state 2. If we look at the values for state 1 and state 2, we can use the different conservation theorems to find our unknown values. So for state 2, x becomes L over 2, which becomes 0.4 meters. We'll call omega 2 simply omega. We wish to solve for that and eventually solve for VR. So we need to find the speed of the rod relative to the tube. So again, the first thing we'll do is the conservation of angular momentum. So the angular momentum about the origin O for state 2 is equal to 1 over 3 times 6 times 0.8 squared plus 4 into 1/3 times 0.8 squared plus 0.8 times 0.4 plus 0.4 squared, and all this is multiplied by omega 2. And so if we simplify this, we get this to be 4.05333 times omega 2. Remember, omega 2 is the angular frequency of the system in state 2, and we don't know what omega 2 is. So that's the angular frequency of state 2 about 0.0. The kinetic energy of state 2 is equal to 1/2 times this value, 4.05333 times omega 2 times omega 2 plus 1/2 into 4 VR squared. We don't know VR, and this simplifies to 2.026667 omega 2 squared plus 2 VR squared. And again, the potential energy V2 is equal to 0. So now we have the angular momentum for states 1 and state 2, state 1 and state 2, and we have the kinetic energy for state 1 and state 2. So we can see that obviously we are going to use the conservation of angular momentum. So angular momentum between the two states is conserved. That is, HO1 must equal to HO2. So this means that 10.6667 must equal to 4.05333 times omega 2. And so we can simply get from here omega 2, the angular frequency, the angular speed at which the system rotates in state 2 is 2.6316, and that's radians per second. And we calculated the kinetic energies before and after. So again, we must apply another conservation theorem, the conservation of energy. Conservation of energy tells us that T1, well, plus V1 must equal to T2 plus V2. Since potential energies are 0, T1 is simply equal to T2. So in state 1, the kinetic energy was 26.667 joules, and this must equal to the kinetic energy in state 2, 2.02667 multiplied by omega 2, which we calculated to be 2.6316 radians per second, and that's squared plus 2 VR squared. So we are left with an equation with only one unknown, which is that VR squared is equal to 6.3158 meters squared per second squared, which means that the speed of the rod relative to the tube, which we wish to calculate, VR, is equal to 2.51 meters per second.